Hello everyone. Thank you for joining this webinar. During this presentation, you will learn how system simulation with SiemensPLM can help you to better design transmission components and better integrate them in the vehicle. My name is Patrice Montalent. I am a business developer for Siemens. I am in charge with promoting SiemensPLM transmission solutions. I have joined the company 10 years ago after a 10 years experience working for OEMs involved in the simulation of conventional, hybrid and fuel cell vehicles. So let's start out by looking at some key trends in ground transportation which make product innovation critical to remain competitive. First, strict regulation push OEMs to reduce the fuel consumption, the CO2 and pollutant emissions of their vehicles. Optimizing performances of the current combustion engines may help to achieve target goals, but new innovative ideas need to be implemented to achieve future regulations. One key disruptive technology that will help meet those goals is vehicle electrification. In the near future, this will be growth in hybrid electric vehicles, but by 2025, there will be regions shifting to purely electrical vehicles. This new technology brings new complexity into the design process, further challenging engineers. With the come of more and more electric components, we can also notice a dramatic growth of controls and electronic systems. Transmissions and drivelines were in the past only mechanical systems. They are now mechatronic ones, combining several physics with electronics and controls. Simultaneously, OEMs and transmission suppliers are more and more global. R&D centers located on different continents have to collaborate. The integration of more and more controls in the systems also generates a need for sharing models and data between the plant design departments and the control design teams. The same tools have to be used by the different sites and contributors in order to reduce the duration and the cost of the project. Last, in order to address local market requirements, the number of variants of the same vehicle is exploding. More and more requirements are defined in order to reach the best level of quality, including the best efficiency, but also the best performances, the best comfort, the best reliability, the best safety, and so on. As it becomes more and more impossible to test physically all the variants, considering all possible scenarios and validating all the requirements, simulation becomes an unavoidable option. Just to illustrate the previous statement, this first graph illustrates the example of pollutant emissions regulations in Europe, which become stricter and stricter regarding NOx, CO, particles, and HC. Euro 2 regulation has been applied starting in 1996, when Euro 6 regulation is the current one for passenger cars. Technologies must evolve very quickly. The second diagram relates to the market shares of hybrid and electric vehicles compared to conventional combustion engine vehicles. Currently, all of the OEMs are already proposing electrified vehicles or have projects for delivering electrified vehicles shortly. The number of sold electrical vehicles will still increase significantly quickly and could reach a third of the new vehicles sold in 2030. Finally, when designing more innovative and complex systems, OEMs and suppliers need to reduce their development time and cost. One way to reach this target is a reduction of prototypes and physical tests. But in order to keep improving the quality of the product when reducing the number of physical prototypes, physical tests have to be replaced by virtual validation. Siemens develops and provides solutions that can help OEMs and transmission suppliers to create a digital twin of their systems, perform simulation, and analyze the results for improving the design when in the same time saving time and money. As already introduced, fuel economy and pollutant emission reduction is a challenge today. But the reduction of the fuel consumption can't be reached to the cost of the driving performances, the driving comfort, or the reliability of the vehicle. So it is mandatory to identify the right balance between all the vehicle attributes: the fuel economy and the emissions, driving performances, drivability, noise and vibrations. So new technologies are implemented in order to reach the goal concerning fuel economy and emissions, such as, for instance, electrification, stop and start, automatic transmissions, with an increase of the gear ratios, but also engine downsizing and downspeeding, vehicle and component weight reductions. All these solutions help fuel economy, but they can also generate negative impact on the vehicle performances, the powertrain reliability, noise and vibrations, the fun to drive, the safety, or the driving comfort. So using model-based system engineering, it is necessary to evaluate the impact of your design choices on all the vehicle attributes in order to select finally the best architecture and solutions. Typically, how can SimCenter AMSIM transmission solutions help you to address these challenges? First, AMSIM is a multi-physics simulation platform, making possible to capture all the physics in the same model and with the same tool. Then, you can predict interactions between mechanical, electric, fluid, and thermal phenomena. SimCenter AMSIM provides an integrated solution combining off-the-shelf models and libraries with a powerful platform. Thanks to the model scalability, you can adapt the level of your model to your design stage. You can select functional models or more physical and accurate ones, from quasi-static models to model capturing transient phenomenon, from 1D mechanics to 3D mechanics, etc. That makes possible to keep the same tool all along the V-cycle of the design process. As you can connect your predictive physical models to a control model or export the plant model to a real-time platform, you can use SimCenter AMSIM for plant design, but also for control design. The SimCenter AMSIM platform provides a large set of tools used to analyze your simulation results, optimize your design, analyze your model in order to simplify it or improve its performances. Application-oriented tools are also available, making the use of the tool easier and faster. Users can also customize the simulation tool in order to deploy it and integrate it still better in their process. SimCenter system simulations makes also possible to better collaborate between departments, OEMs, and suppliers. Finally, SimCenter AMSIM is designed in order to reach the user expectations and help him to design the best quality product easier, faster, and reducing the development costs. What are the typical engineering problems you might address thanks to SimCenter AMSIM transmission solutions? First, we can state that it depends if we consider a transmission supplier or a vehicle OEM. SimCenter AMSIM can help suppliers to evaluate and optimize the performances of their components, usually with quite detailed models, integrating a high level of physics. SimCenter AMSIM can also be used in order to design, validate, and pre-calibrate controls of the component actuators. SimCenter can also be used by the suppliers in order to convince an OEM about the capability to improve the performances of his vehicle thanks to the integration of a new component. Using SimCenter AMSIM, the OEM can, on his side, evaluate easily, quickly, and at low cost a supplier component, without integrating the component physically in a prototype. Using system simulation, the OEM can balance all the vehicle performances: fuel economy, drivability, NVH, safety. It can perform a large set of simulation, including the evaluation of different architectures and components, considering different scenarios. The OEM can also use SiemCenter AMSIM in order to design the best control strategies for the supplier transmission. But can the supplier really evaluate the performances of its component without evaluating its behavior in the vehicle? Can the OEM evaluate accurately the performances and the behavior of the whole vehicle without a detailed model of the components? More and more, OEMs and suppliers are exchanging data and models. SiemCenter AMSIM makes possible to share encrypted models in order to predict the intellectual property when sharing models. Let's now talk more into details about SiemCenter AMSIM capabilities for transmission design and integration. First, for the estimation of performances and losses, models are usually quasi-static models. These models do not need to catch high-frequency phenomenon. SiemCenter AMSIM provides the required capabilities to support design of every type of transmission, integrated systems and subsystems, reduce ground vehicle fuel consumption and improving performances, optimize the system design and actuation, predict the behavior of the transmission at any operating point, including, for instance, different thermal conditions, and run multi-attributes optimization at each development steps using variable models complexity. Thanks to these capabilities, transmission suppliers and OEMs can drastically improve the performances and losses of their systems, reducing in the same time the cost and the duration of their project. Many OEMs and suppliers are already using SiemCenter AMSIM for performances optimization and losses reduction. For instance, the German supplier Voigt Turbo uses SiemCenter AMSIM to predict the dynamic behavior of transmission systems and subsystems. They can, for instance, reduce testing time and number of prototype iterations when improving the design of the hydraulic valves used to actuate transmissions. Thanks to SiemCenter AMSIM, Punch Powerglide can rapidly test different configurations to balance performance, comfort, and efficiency. Punch Powerglide could reduce transmission lubrication circuit design time from months to weeks and better controls noise and vibrations. Using SiemCenter AMSIM, BorgWarner can predict without physical testing the response time at different temperature of intelligent all-wheels drive system. They can also analyze pressure fluctuations and pulsations in the actual piston pump used to actuate the system. Finally, system simulation helps them to significantly improve the performances of their systems while reducing the number of prototypes, testing cost, time, and efforts. Let's now demonstrate some capabilities of the simulation tool. We will now consider a vehicle using a manual transmission. Let's now demonstrate some capabilities of the simulation tool. We will now consider a vehicle using a manual transmission. If we want to improve the design of the gearbox in order to improve the fuel efficiency of the vehicle, then which component in the transmission do we really need to modify? Can we identify quickly which modifications will have the most efficient impact on the reduction of losses in the gearbox? SiemCenter AMSIM makes possible to model into detail the transmission, considering each gears and the bearings. The user can then select gear and bearing submodels, evaluating component losses, taking into account the operating points, especially the load and the velocity. For instance, one can predict gear contact, rolling and padding losses from the geometry of the gear and the lubricant properties. So if we run a simulation, we have access to the different value of the losses all along the simulation. We can plot all of them in order to evaluate the evolution of these losses. But we can also, using some post-processing tools, identify which component in the system produce the higher level of losses. So the most important losses will be generated, in this case, at the level of the vehicle, with the aerodynamic losses and the rolling resistance of the tires. But if we expect the vehicle, we can identify that significant losses are generated at the level of the differential, or for instance at the level of the 6 gears. We can, for instance, plot the value of these losses in order to compare the losses generated by the different components. So we can see here the losses of the differential, the losses of the 6 gear. Once we have identified the component generating the higher level of losses, we can also in SiemensPLM open an app dedicated, for instance, here to the gears. So here is the app dedicated to the differential gear set. So we can visualize the main parameters, we can visualize the geometry, we can visualize also, for instance, the predicted losses depending on the velocity and the torque for friction losses or padding losses, for instance. Using this app, we can also modify some parameters in order to evaluate what would be the impact of these modifications on the different losses. We can on this graph plot also the operating point of the gear set during the simulation, and so we can see finally the impact of the number of teeth of the gear on the losses. And if we perform a new simulation with a modified design, we will be able to evaluate what is the impact on the global fuel consumption of the vehicle. We can still go deeper in the analysis with connecting the models of the gears and the bearings with thermal models. In that way, it is possible to also evaluate the impact of the temperature on the losses of my system. And we can also use some dedicated post-processing tools in SiemensPLM in order to analyze the simulation results at the end of a simulation, in order to visualize very easily and quickly what is the impact of the operating point regarding the torque, the engine torque, the engine velocity, and also the transmission temperature for each of the gear sets. So for instance, we can identify here the impact of modifying the temperature from 40 degrees to 80 degrees on the roller bearing losses, the synchronizer rings losses, the journal bearing losses, the gear padding losses, and the gear contact losses. We can also compare, for instance, the losses of the transmission, the gearbox, if the torque is 30 Newton meter or 150 Newton meters. After performance and losses, let's now consider the drivability attributes of the vehicle. Predicting drivability requires models capturing more dynamics with a frequency range going from a few hertz to a few dozen of hertz. SiemensPLM provides the required capabilities to select the right architectures and design solutions early in design in order to improve the vehicle drivability. Optimize all plant subsystems and controls integration, ensuring smooth and steady accelerations, best of class shift quality. Thanks to these capabilities, Transmission suppliers and OEMs can drastically improve the vehicle drivability using measurable criterion, reducing in the same time the cost and the duration of their projects. Many OEMs and suppliers are already using SiemCenter AmSim in order to provide the best drivability and driving pleasure to their customers. For instance, the French OEM Renault has completely integrated SiemCenter AmSim in the powertrain design process. Thanks to the simulation tool, Renault can use transmission virtual design while the hardware is still in development and no prototype is available. It makes possible to identify any need for modifying the transmission and relative controls early in stage design, reducing the impact on cost and delay. Renault can finally achieve optimal powertrain performances, cutting the development time almost in half. In the same way, General Motors could, thanks to SiemCenter AmSim, reduce the number of transmission prototypes, get a shortened time to market, front-loading transmission controls engineering with SiemCenter AmSim. The Japanese transmission supplier Aisin AW has deployed a full vehicle model-based approach for the prediction and elimination of clutch judder. Thanks to accurate predictions, they can increase passengers' comfort. Let's now demonstrate some capabilities of the simulation tool regarding drivability, considering a model of an automatic transmission vehicle. This model can be used in order to evaluate the behavior of the vehicle, considering scenarios as a gear shift, a vehicle takeoff, a tip-in, a tip-out. In order to evaluate drivability with the right level of accuracy, we need a model able to catch more dynamics than the one used for fuel economy or performances. Thanks to SiemCenter scalability, we can easily select models that will predict the torsional deformation in the driveline, taking into account the shaft and the friction component's stiffness, but also the stiffness and the damping generated by the tires and the suspensions, considering a 3 degrees of freedom vehicle model. Such a model can take into account the longitudinal motion, but also the vertical one and the pitch. In this model, we will also consider the reaction of the powertrain on the car body through the engine mounts, using a 3D model for the engine block. If we simulate this model, we can plot some results, and for instance, we can visualize during the gear shiftings or during the vehicle takeoff, here in this part of the simulation, what is the impact on the car body longitudinal acceleration or the car body rotary acceleration. And we can visualize that thanks to good level of model, we are able to catch the dynamics and the oscillation of the vehicle during the takeoff and during the gear shiftings. We can also use in AmSim a tool that will be able to evaluate the different attributes of the vehicle, and if we perform a simulation also in order to evaluate the fuel consumption and the performances of the vehicle, these apps will make possible to identify the right balance between all the attributes of the vehicle, performing some batch simulation, for instance, comparing different stiffness for the engine blocks or different controls for the gear shiftings. So for instance, we can evaluate the impact of modifying the stiffness of the engine mounts, and as we can think it will have no significant impact on the fuel consumption or the performances of the vehicle, but it will have an impact on the drivability during tip-in and tip-out, for instance. Now let's still increase the level of frequency in the vehicle model in order to address noise and vibrations. SiemCenter AmSim provides the required capabilities to predict torque oscillations generated by an engine or an electric motor, by gear shocks, by friction phenomenon, or system actuations, for instance hydraulic actuation. Oscillation can also be generated by the coupling between the mechanical system, the hydraulic actuation, and controls. SiemensCenter AMSIM makes possible to identify the natural frequencies of the driveline and predict how these eigenmodes are excited by torque oscillation sources. SiemensCenter AMSIM also provides models used to design components such as clutch dampers, dual mass flywheels, centrifugal pendulum absorbers. Thanks to these capabilities, transmission suppliers and OEMs can drastically reduce noise and vibration and improve the quality feeling of the vehicles, replacing expensive and time-consuming physical tests with virtual evaluation, reducing in the same time the cost and the duration of their projects. Many OEMs and suppliers are already using SiemensCenter AMSIM in order to design the best reduction of noise and vibration. For instance, Lamborghini uses SiemensCenter AMSIM to predict torsional vibrations in drivelines and optimize them, reducing the number of prototypes. Cummins and Allison transmissions have used SiemensCenter AMSIM for troubleshooting. It helps them to get a better understanding of coupling effects between the engine and the transmission and identify the best solutions for getting rid of vibration phenomenon. Thanks to SiemensCenter AMSIM, punch powertrain can avoid risk of a redesign after design freeze by front-loading potential booming noise assessment. Using system simulation also helps them to ensure a smooth integration of the transmission in the full vehicle. Renault uses SiemensCenter AMSIM for better design and integration of a dual mass flywheels in the driveline. Simulating different scenarios, they can better understand complex phenomenon and reduce analysis time significantly compared to test-only studies. Let's have a look to an AMSIM demo where we will consider the complete driveline of a vehicle, starting from a 3-cylinder engine to the wheels. So at the left side of the sketch, we have models used to predict the torque oscillation generated by the combustion engine. So the torque oscillation will be mainly generated by the pressure, the peak of pressure in the piston, but also the rotating masses in the crankshaft and the piston at the level of the crankshaft by itself, the connecting rod, the piston. And also torque oscillation will be generated by the torsional behavior of the crankshaft. You can see here an app which is dedicated to the cylinder and crankshaft submodel, and that helps users to define parameters easily and faster. So if we perform a simulation with such a model, we can we can use some plot in order to better visualize the behavior of the engine in the frequency domain. So we can, for instance, visualize here the spectral map with the different orders of the engine, and we can also use some order tracking. At the right side of the combustion engine, we have also integrated in the sketch some components used to simulate the behavior of a dual mass flywheel and a CPVA. So for the dual mass flywheel, we also have in AMSIM a dedicated app that helps the user to define easily and quickly the different parameters of the components. For instance, in order to define the stiffness of the different level of arc spring in the dual mass flywheel, and also some parameters defining the geometry of the component. Then performing a simulation, it's possible to optimize components such as the DMF or the CPVA and evaluate what is the impact of their integration in the driveline on the global oscillations and oscillations that will be propagated in the driveline. Now, what's about electrification? How SimCenter AMSIM can help you to address this challenge? Thanks to model scalability, SimCenter AMSIM makes possible to capture any level of frequency domain. For batteries, electrical motors, and power electronics, you can find quasi-static models, but also mean-level models and high-frequency models. Then, SimCenter AMSIM provides the required capabilities to select the right architectures for the hybrid or electrical vehicles, the right components, and design solutions early in stage design. Optimizing all plant subsystems, motors, power electronics, batteries, supercapacitors, fuel cells, and control integration. Optimizing thermal management of electric devices, replacing expensive and time-consuming physical tests with virtual evaluation. Using multi-attribute criteria for comparing vehicles' performances and NVH attributes. Many OEMs and suppliers are already using SimCenter AMSIM in order to design hybrid or electric powertrains and integrate them in vehicles. For instance, Continental evaluates, thanks to SimCenter AMSIM, the impact of thermal management strategies on vehicle performance. Especially thanks to the multi-physics platform, they can compare different battery heating and cooling methods. In that way, they can shorten the duration of their project and increase the vehicle driving range. With SimCenter AMSIM, McNash Tire can analyze easily different hybrid vehicle architectures and operating strategies. They can maximize the design efficiency with minimum development cost. Siemens e-car use AMSIM to predict the efficiency of required powertrain electric components, validate technical choices early in the design cycle. The Lion Electric Company uses SimCenter AMSIM to validate different electric drivetrain concepts and driving scenarios early in the process. Thanks to multi-physics libraries, they can study interactions between mechanical, electrical, thermal, and vibration phenomena. They can also better integrate supplied components like batteries, heat exchangers, door mechanism, and so on. So in this last demo, I will show you how SimCenter AMSIM can be used in order to get all the benefits from electrification. Integrating electric motors in the driveline makes possible to recover the kinetic energy of the vehicle during accelerations or to optimize the engine operating point. Then it helps to reduce the vehicle fuel consumption and the pollutant emission. But electrification can also be used to improve performances, drivability, and safety. So let's, for instance, consider the integration of an electrified rear axle unit as the agility rear axle promoted by Linamar on its website. So you can see here a copy of the web page, Linamar web page, and on this web page you can find some information about the system. So it can be integrated on a conventional front-wheel drive vehicle. It features twin independent 75 kilowatt motors coupled with a single speed reduction bolted to their respective half shaft. It is coupled with a 330 volt battery and enable all electric driving up to 130 km per hour. But it also enables an all-wheel drive mode. And as the twin motors can be controlled independently, torque vectoring is also possible, increasing handling and safety. So from this information provided on the web page, it's possible to evaluate in the first step the fuel economy that can be provided thanks to this system. So we can model two vehicles. At the left side we have the model of a conventional vehicle, and at the right side we have the model of the same vehicle but integrating on the rear shaft the agility subsystem. And if we perform simulation with this model, if we take care about the final state of charge of the battery at the end of a drive cycle, we can evaluate the difference of fuel consumption between the two vehicles. And we can identify, in this case, for a 10-15 mode drive cycle, that the fuel economy is close to 38%. So it is quite significant. Now we can use a second level of model for the same vehicle in order to evaluate the impact of the torque vectoring. So we can apply, for instance, a sinusoidal wave on the steering angle and compare the behavior of the vehicle with or without using torque vectoring, thanks to the electrical motors. So we are now using a 3D model of the vehicle, making possible to predict the vehicle 3D dynamics. And if we simulate the model, we can easily compare the behavior of the vehicle with or without the torque vectoring regarding, for instance, the lateral acceleration of the vehicle, the car body side slip, or, for instance, the car body roll. So the red curve is a conventional vehicle or the vehicle without torque vectoring, when the blue curve is the result with the torque vectoring. So we can see that the performances are improved. We could also use such a model in order to evaluate, for instance, the behavior of the vehicle with the loss of adherence on one wheel. Finally, let's recap some of the good reasons to select SimCenter MSim for transmission design and integration. SimCenter MSim is a best-in-class mechatronics simulation tool, providing a large set of multi-physics and applicative models and libraries. SimCenter MSim makes it possible to optimize the transmission components design, but also integrate them in the whole vehicle and with the controls. Multiple demos are included with the software. Users don't have to start from scratch for building a new model, but can use these demos as templates. All the demos presented in this webinar are standard or based on standard demos available within SimCenter MSim. Thanks to application-oriented apps, analysis and visualization tools, users can still build and simulate models easier, accelerating the design process. Thanks to its 30 years experience with system simulation, Siemens can totalize more than 800 innovative companies using SimCenter MSim, including most of the automotive OEMs and transmission suppliers. Siemens regularly integrates new features in the simulation software and supports closely SimCenter MSim users in order to satisfy customers. Thank you for watching. For more information, do not hesitate to visit our website or to contact your local Siemens office.